Yes, okay. Everybody is in or creeping in. Okay, thank you all for coming today. It is my great pleasure to introduce Karin Fischer. Karin comes to us from Brown University, where she is the Elizabeth Scherck Distinguished Professor of Geosciences. Karin's pedigree is wonderful. She got her undergraduate degree at Yale University and her graduate degree at MIT. Karin has won a wide assortment of awards over the years. She's a fellow of the American Geophysical Union. She was the 2016 Benno Gutenberg Lecturer for the Seismology section of AGU. And this year, she was awarded the Harry Fielding Reed Medal, which is the Seismological Society of America's highest honor, which is to be awarded in late April, assuming that there actually is an SSA this year. I'm assuming they'll give you the award one way or the other. Karin and I worked together doing a seismic deployment in the southeastern US in sort of the 2010 to 2014 time range. We had many adventures, also with Ved, who's in the audience here somewhere. And in particular, for those of you who know the work that I've been doing with direct variable instruments, we ventured into trying to use existing equipment for direct burial and quickly learned the hazards of that. So there is a benefit to specialized equipment. Karin has done a lot of work on the lithosphere-asthenosphere boundary, but I think today she's going to be focusing on the oceanic LAB largely. And so with that, I will let you take it away.
So thank you, Laura, for that very kind introduction, and it's great to be back here. I think so. Okay. Can you all hear me okay? Okay. It's wonderful to be back here. So today we're going to be taking a tour of several case studies to look at variation in lithosphere-asthenosphere properties. And the basic question that I'd like to get at are, what are the physical and chemical properties that differentiate the mantle part of the lithosphere from the asthenosphere? Essentially, why do we have lithosphere that acts plate-like? Why do we have relatively rigid lithosphere? And this schematic illustrates some of the main ideas. The brown layer is meant to represent the crust. This blue layer is meant to represent the mantle part of the lithosphere. The red is the asthenosphere, which presumably is advecting past the lithosphere in some fashion. And why is the lithosphere strong relative to the asthenosphere? Well, part of the reason is that it's colder. We know that for sure. So the lithosphere is colder. It makes it more rigid than the asthenosphere. But there are also chemical effects. A lot of xenolith evidence and also just what we know from mantle melting would suggest that melt depletion has changed the composition of the mantle lithosphere, which would make it higher velocity, but significantly that it would also make it drier. And a drier mantle will also be a more rigid, stronger mantle. But then in addition, certainly in some regions, there's evidence for partial melt at the top of the asthenosphere, potentially that can pool and collect at the base of the lithosphere. And that's another property that can produce the contrast in properties. So what we really want to get at is the compositional and physical properties, temperature. But what we're left with as seismologists are seismic properties. And in particular, we'll be looking at seismic velocities. And here I just want to make the point that while we're measuring changes in seismic velocity, in particular, we'll be looking at changes in shear wave velocity. They actually do contain a lot of information about the properties that I just described to you. So let's say that this schematic here shows a geotherm, a plot of temperature with depth. Here's the mantle adiabat. This is a very gradual transition. We would expect that to produce a gradual decrease in mantle viscosity and also a gradual decrease in shear wave velocity. So typically, purely thermal models are going to give us relatively gradual gradients between lithosphere and asthenosphere. But let's say we now make the lithosphere more depleted. We change its composition relative to the asthenosphere, and in particular, we make it drier. We then might have a profile that looks like this brown line here, where the lithosphere has a higher velocity and a higher viscosity and a sharper transition into the weaker asthenosphere. And then if we add a little bit of partial melt into the top of the asthenosphere, which pools below the base of the lithosphere, we can get a bigger kick that decreases velocity still further, and also that decreases viscosity still further. And that would have important implications for how the lithosphere couples to the underlying asthenosphere. So that's what we're going to be trying to get at. With these properties in mind, we also have to remember that mantle grain size plays an important role in determining both mantle viscosity and mantle velocity, and we need to keep an eye on the effects of deformation fabrics and the anisotropy, the directional dependence in wave speeds that they produce. Okay, so we're going to look at 4 case studies. We're going to start by looking at the tectonically active western US. Then we're going to turn our attention to the old part of the continental lithosphere cratons. Then we're going to look at some new work in the subduction zone in Alaska. And then we're going to look at the oceanic lithosphere. And the title of today's talk, Global Extremes in Lithosphere-Asthenosphere Properties, I actually made that up when I thought the 4th case study was going to be looking at Anatolia. I'm not going to talk about that because we have some new work on the oceanic lithosphere that I'm particularly excited about, so Anatolia got bumped. But if you're wondering where the global extremes came from, it's because in Anatolia, the lithosphere is really thin and the asthenosphere is really hot, so that's a global extreme. But I'm not talking about that today, but you can ask me about it later. So I want to recognize a wonderful group of students and postdocs whose work you'll be seeing: Emily Hopper, who was a Ph.D. student at Brown, who's now a postdoc at Lamont; Zach Alon, who did a postdoc at Brown and is now on the faculty at UC Santa Barbara; and 3 current Brown graduate students, Jinlin Hua, Hannah Krieger, and Isabella Gama. Okay, so let me just briefly describe the 2 main tools we're going to be using in this talk. So we're going to take a bit of a dive into seismology so you understand the methods, and then we're going to come out and use those methods to study lithosphere-asthenosphere properties. So one tool that we use are converted seismic body waves. So let's follow this ray here. This shows the path of an S wave that converts to a P wave at a contrast in velocity and then makes its way to the station. I know some of you in the audience have used P to S phases extensively, so this would be a P wave that converts to an S wave. In any case, when one of these converted body waves hits one of these boundaries, it generates a new converted or scattered arrival. And then we can take the relative time of that new arrival with respect to the parent phase, and we can use that timing to infer the depth of the boundary. So for example, here's an example of an S to P receiver function. So here's the boundary between the crust and the mantle lithosphere. This would correspond to an increase in shear velocity. That would produce a positive phase in the way that we're displaying the data here. So this positive bump would be the MOHO. Now, if we have a velocity decrease between the mantle part of the lithosphere and the asthenosphere, so this is now a drop in velocity, we would get a negative phase, and that's shown by this arrival here. But here I'm also illustrating another important property, which is depending on how compressed in depth the velocity change is, you're going to get a difference in phase amplitude. So in particular, if we take a 10% velocity decrease and distribute it over 0 kilometers, basically a step function, we get a large, narrow negative phase. But if we take that boundary and we distribute it over greater and greater extents in depth, say, for example, the orange line is 30 kilometers, you see the phase has gotten broader and weaker. And by the time we get to distributing that 10% over 70 kilometers, the phase is now much weaker and harder to observe. So that property is going to be important when we're talking about the boundaries that we'll be imaging. So this is just an example of S to P common conversion point stacking. And Ved Lekich is in the audience. He is the person who actually wrote our first CCP stacking codes. So shout out to Ved, who's sitting right there. So basically how CCP stacking works is you take the converted phases recorded at stations at the surface. So you have the energy as a function of time. and you can project it backward along its ray path to potential conversion points. And then when you want to stack the energy at any particular point, you can use what we know about the physics of the wave interaction to come up with a reasonable way of averaging the energy for all the rays around that point to get the best representation of what the scattering from that point would be. And this is an example from a study by Heather Ford in 2013. So this is showing a grid of nodes in 2D at the surface. Imagine that this extends down into the Earth in depth. And then we're constructing a stack of the scattered energy in 3 dimensions. And this sort of ratty red energy is not a very good MOHO, but that's the velocity increase between the crust and the mantle. And just to show you where this profile is, it runs down the eastern edge of the great dashed line is where the MOHO would be from studies that use P to S data and also active source data. So basically methods that in this particular setting are better set up for the MOHO. A lot of the shallower energy here is from the base of sedimentary basins. So the Great Valley has a lot of sediments in it, and the base of those sediments also produce converted wave energy. Yeah, so basically in this study, pay attention to the mantle, ignore the crust because it's not very good. Okay. So one of the things that we've been working on a lot in the past few years is trying to better incorporate the physics of the interaction of these converted waves with boundaries into the way that we construct our images. And this is a figure from a new paper from Junlin Hua. What is being shown here, in each of these surfaces, we're looking at what we call a sensitivity kernel. This is a surface that represents part of the sensitivity kernel. So a way of thinking about this is the red line shows the path of the energy. Here it's an S wave, here it converts to a P wave, and it makes its way to the station. So we're interested in imaging the structure around the conversion point. However, one of the oddities of these S to P phases is that the energy that makes its way to the station from this point arrives at the same time as the energy from everywhere on this surface. So we need to account for that when we construct our CCP stacks or when we use these phases in imaging in any way appropriately. And because of this very flat shape, particularly up here, S to P phases are really good for getting at quasi-horizontal discontinuities, discontinuities with dips of less than 15 degrees. And Ved had a very nice paper from about 2 years ago that also illustrated this. So that's S to P. For those of you who've worked with P to S, the sensitivity kernels have a very different shape. They're sensitive to structure, much more local to the station. And because of those steeper angles, they have better sensitivity to higher dip angles. So I'm not going to go into this in detail. Anybody who's interested in the nuances of the seismology, I'd be happy to explain this more. But I just wanted to point out that there's some really cool wave physics in here, and we're bringing that into our methods. OK. So the second type of tool we're going to be using are joint inversions that take the scattered body waves, S to P phases and P to S waves, and jointly invert them with Rayleigh wave phase velocities. So Rayleigh waves are surface waves. They're waves that are trapped in the relatively shallow layers of the Earth, and they can make multiple circuits around the Earth. So they are very good tools for getting at absolute shear velocity, but they're really poor tools for getting at interfaces. So in these joint boundaries, in these joint inversions, we're combining the converted body waves to capture the interfaces, and then we're using the surface waves to get the absolute velocities. And this set of plots illustrates the idea here. So each of these is an inversion for a one-dimensional velocity model. And the input model is shown by the black line here. It has a crust. It has a high-velocity mantle lithosphere, and then a very sharp transition into the asthenosphere. And each of these panels shows an inversion with a different kind of data. So here we're inverting just the Rayleigh waves alone. And what I want you to pick up from this is that the Rayleigh waves do a pretty good job of getting at the absolute velocity. So we've taken the black model, we compute synthetic data from that model, and then we invert that synthetic data to see what we can resolve back about our input model. So what we hope is that the colors, which represent basically the family of models that best fit the synthetic data, where those colors are warm, we have a higher probability of a given set of model parameters. So where the colors are warm, you can think of that as the family of best fitting models. And if you compare the best fitting models from this inversion to the black input model, you see that we're getting absolute velocity pretty well, but the Rayleigh waves do a terrible job of capturing the interfaces. If we take the S to P and P to S phases by themselves, they do a pretty good job of capturing the interfaces, but you see the absolute velocities wander all over the place. They're not good at getting the absolute velocities. But just to cut to the chase, when we combine the surface waves and the converted body waves, say, for example, in this inversion here with just S to P and Rayleigh waves, we get the MOHO and the lithosphere-asthenosphere transition quite well, and we also have our highest probability of acceptable models tracking the absolute velocity well. So that's an approach that we're going to be applying in the talk. So before I move on, are there any questions about the methods? Yeah, so at the bottom of the model there, we have no converted body waves from that depth. And so we're only relying on the Rayleigh waves to get the absolute velocities. And there the kernels are quite broad, the sensitivity kernels that describe how a Rayleigh wave at a long period is going to basically reflect Earth structure. So they do wander around a little bit at depth. I will say all of these cases were with relatively high noise levels. This one over here was dropping to a noise level, which actually probably is more consistent with what we have in most of our data. And there we're tracking the velocities at depths a little bit better. But yeah, I mean, that is a concern. OK. So first, let's take a look at the US. So this is now showing a map where each black and gray dot represents a broadband station. We have both permanent stations from the permanent networks in the US. We also have these black dots, which represent the EarthScope transportable array, which covered the US until about 2014. I think the last station came out. And this is really a remarkable data set to try to image lithosphere-asthenosphere properties beneath the lower 48 states. So we have these seismic stations. We're taking earthquakes at distances of 30 to about 100 degrees away, so teleseismic sources recorded at these stations. And the first thing I'm going to show you are the results of a common conversion point stack. So this is work from Emily Hopper. So this tectonic map shows the locations of several profiles, and I'm showing you this profile here through the somewhat southern US. So this is now depth on this axis. This is longitude on this axis. And some tectonic terrains are labeled at the top. And what you see pretty clearly is in the western part of the US, beneath the basin and range, we have this very, very strong negative arrival. As we move into the cratonic US, this arrival dies out. We have relatively spotty energy in this depth range. This red energy is a poorly realized MOHO. And then when we come out the other side in the eastern US, we have negative energy in the depth range of about 70 to 100 kilometers. It's not as strong as the western US, but there's definitely a coherent signal there. So how can we interpret all of that? So this profile was actually E prime. Okay, I'll show you DD prime a little bit later. I think that's the one closest to where we are today. So this is taking, there are many wonderful tomographic models of North America. This is just taking one from Schaefer and Lebedev, taking their VS tomography. And in Camarano and Guri, this model was converted to a thermal thickness of the lithosphere, and that's what's shown by this dashed line there. It's essentially just taking the tomography, fitting it with a conductive lithosphere over an adiabatic mantle, and saying that that change in slope of the geotherm would correspond to the lithosphere transition. So completely independently, this model shows a lithosphere-asthenosphere transition that falls very close to this very strong negative phase we see here. So Putting the two together, you can think of this as the lithosphere-asthenosphere transition in the western US. When we get into the craton, the lithosphere is much thicker. This is a depth slice of shear velocities at 150 kilometers, and you can see the crotonic lithosphere is expressed by these much higher velocities beneath the crotonic regions of the US. That corresponds to a thicker lithosphere beneath this part of the profile. This model doesn't really resolve the thinner lithosphere beneath the Appalachians very well, but there is thinner lithosphere there. Laura Wagner and others have done very nice regional tomography studies that would suggest a lithosphere thickness that again agrees with this boundary. So here we have lithosphere-asthenosphere boundary. Here's the base of the lithosphere, not a lot of scattered energy, and then a booming strong transition in the western US. This is now showing 3 other profiles. This one here is DD prime, and I put a star on it. This is actually about 150 kilometers south of DTM, but this is the profile that's closest to us here. And so we're sitting above the somewhat stronger lithosphere-asthenosphere transition in the eastern US. But on all of these, you see a similar pattern. Very strong boundary in the western US, not much energy from the base of the lithosphere beneath the craton, moderately strong lithosphere-asthenosphere transition in the eastern US. And in some of these, you see a fair amount of coherent energy within the body of the crotonic mantle at depths of about 7,200 kilometers. So there's some in the superior craton that's pretty strong, but on other profiles, for example, this more southern profile here, it's a lot weaker and less continuous. And we'll come back to this feature a little bit later. So now let's turn to the joint inversions. This is just illustrating the same thing that you saw, but now in terms of shear velocity models. So this is the 1D shear velocity model beneath the station near the old end of the high lava plains in Oregon. You see a very, very thin mantle lithosphere and a very rapid transition into an asthenospheric layer. For reference, these curves show global averages from the French and Romanowitz, French et al. 2013 SEMMA model. So this is the green profile for 0 to 25 million year old lithosphere. And this part of Oregon basically looks like really young oceanic lithosphere. So very thin lithosphere, very low velocity asthenosphere. Contrast that with station EYMN up here in Minnesota. Here we have a much higher velocity crotonic mantle lithosphere that extends to depths of more than 200 kilometers. So this is again just contrasting the very thin lithosphere with a sharp lithosphere-asthenosphere transition in the western US relative to the thick lithosphere with a very gradual transition at its base beneath the craton. Okay, so now that you have that continental context, let's take a look at what we can infer about processes of melt influx into the base of the lithosphere beneath the western US. So to do this, Emily modeled the velocity gradient associated with the lithosphere-asthenosphere transition everywhere where we could find sort of a well-identified lithosphere-asthenosphere boundary S to P phase. So this is from the CCP stack. So if we look at the schematic, this is velocity, this is depth. Here we have a velocity change from the lithosphere to the asthenosphere. So properties of interest are the depth of that boundary. That's what's shown here in this plot. The velocity contrast associated with that velocity gradient, that's what's shown in the middle profile here. And then the depth interval over which that velocity contrast is distributed, that's shown in the lower map. And if you look at the western US, and you take the average velocity gradient, you get about a 10 to 12% velocity drop over about 35 kilometers in depth. And that is actually a huge and relatively sharp velocity contrast. If you compare that to velocity models that have purely thermal gradients, you cannot achieve that velocity gradient with a purely thermal model. So that's our first clue that at the base of the lithosphere in the western US, there must be some collected melt at the top of the asthenosphere. Now to probe what that might look like, Emily then took the NAVDAT database, and what she's made a plot here is the time since the earliest or the youngest magmatism across the western US. So just simply taking the NAVDAT database and saying, when was the last eruption of some kind of surface magma somewhere in the western US? And then she took these properties and correlated with them with the time since last magmatism. And we end up with this comparison here. So this shows the age of the interval we're looking at. The deep red line is the youngest depth, or sorry, the youngest age bin, 0 to 2.2 million years, or 0 to 200,000 years. And then we have progressively older and older and older magmatic ages represented by the other colors. So this plot shows the amplitude of the phase generated from the lithosphere-asthenosphere transition. This shows the breadth of the transition and depth. This shows the absolute depth of the transition. And then this plot shows the mean VS in the uppermost mantle. This is from the Schmanton-Lynn velocity model. And basically, there's a fair amount of complexity in here, and there's not a lot of coherent signal except for two things. Two things stand out. The first is if you look at the amplitude of the S to P energy scattered from that boundary, you see that the youngest, or the phases that correspond to the youngest magmatism, this deep red line here, are skewed to lower amplitudes. The second thing we see, you can't see much in this one, can't see much in this one. The second thing we see is that in that same 0 to 200,000 year age range, the velocities in the lithosphere are also somewhat lower. So when we put that together, we get a picture of melt introduction into the lithosphere that looks something like this. So here we have unmodified lithosphere and asthenosphere. Then we have a melting event, some influx of melt. So melt rises into the base of the lithosphere. As it's rising to the surface, where it's expressed as surface magmatism, it basically is erasing the velocity contrast between the lithosphere and the asthenosphere. So we're making that contrast much weaker, so we don't see a phase that is as strong, okay? And the other thing is that the influx of melt also reduces the average velocity of the mantle lithosphere. So those are the two effects that we saw. Then, as you know, the melt event is over and the system cools, you can imagine that the lithosphere cools, the melt maybe freezes a little bit in place, whatever's left in the lithosphere. But in any case, the lithosphere, again, becomes somewhat colder, somewhat stronger, somewhat higher velocity. And we produce a thin layer of residual melt at the top of the asthenosphere and the base of the lithosphere. And then that produces the stronger phases that actually typify much of the western US. So the signal of melt is actually to make that boundary weaker. But the interesting thing is it seems to be a relatively ephemeral phenomenon. Within about 200,000 years of that melt event at the surface, the effect is gone. And that part of the lithosphere looks more or less like the other relatively recently magmatically active parts of the western US. So 200,000 years, and then the effect goes away. Okay, so that's one thing that we've learned. Okay, so now let's turn our attention to the cratonic lithosphere-asthenosphere transition. So now let's focus on profile BB prime, which is a little bit farther north. And I've already pointed out to you in the CCP stack that at the depth where we would expect the base of the lithosphere from tomography, there's not a lot of scattered S to P energy, not a lot of converted S to P energy, but we do see these relatively pronounced phases at depths of about 70 to 100 kilometers within the body of the lithosphere. So that's what we see in the CCP stack. If we now look at velocity models, so here's the profile from Oregon that I already showed you. So this is in the tectonically active western US, so not craton. But these three, 1, 2, 3, are from cratonic regions. This is RSSD from the eastern Wyoming craton, and then ECSD and EYMN from the Superior craton. So you've already seen this profile. This appears to be a portion of the cratonic mantle lithosphere where we have thick, high velocity lithosphere, a very gradual transition at its base. This is so gradual, you're not going to produce S to P converted waves from this gradient. And there's not a lot going on in the shallower mantle. At this station, we have 2 actual velocity reductions in the lithospheric mantle, but again, a very gradual base. And then at station RSSD, we have a very large velocity reduction in the mantle and a somewhat sharper velocity gradient at its base. Overall, when you look at these profiles from the cratons, typically the base of the lithosphere, the transition into the asthenosphere, is in fact very gradual. You know, it's some number of percent, maybe 4 to 3% velocity contrast distributed over 60 kilometers or more, so very gradual. But there are some spots where the transition seems to be a little bit sharper, and that could be a place where another effect, maybe volatile enrichment in the mantle, or potentially even a little bit of partial melt that's collected there, could be sharpening up that velocity contrast. So that's what we see from the cratons. So overall, when we're thinking about the cratonic mantle, a way I like to think about it is, yes, indeed, we know from xenoliths that we have a depleted layer in the cratonic mantle, a chemical boundary layer. But what we seem to be seeing in terms of the lithosphere transition is essentially a thermal halo around that chemically depleted zone. And this is the very gradual velocity gradient that the seismic waves typically pick up on. And then this is just a model from Cooper et al. 2004 showing a similar thing where this is a chemically depleted cratonic root. And then these darker colors here show a band of lower temperatures. Again, just one way of modeling that thermal boundary that the seismic waves seem to be seeing. I started at 11, is that right? Okay, good. Just keeping track of time. Okay. Alrighty. So beneath cratons, the lithosphere-asthenosphere transition is really gradual. But what about these bands of negative arrivals that we see in the shallower mantle? Now, this could actually be a whole talk by itself. And I'm just going to zoom through this really quick, but I put it in because I know there are some people in the room that find this topic interesting, but there's a lot more to this. So if it sounds like I'm going fast, it's because I am going fast. There's actually been some controversy about whether these mid-lithospheric arrivals, these mid-lithospheric discontinuities exist. So Hannah Krieger, a wonderful graduate student at Brown, has done a very, very careful global survey. These are just showing examples, 4 of the many stations that she's looked at. So the red arrival shows the MOHO. These blue arrivals here show mantle energy. And what we see is at some stations, for example, RSSD that I already showed you in North America, there's a pretty strong arrival. This corresponds to about a 6% reduction in shear velocity at a depth of about 80 kilometers. We also see similar arrivals at many other stations. They tend to be more on the periphery of cratonic cores. But then there's some stations like this station in Europe, BRVK, where the mantle is completely quiet. There is no velocity contrast in that depth range that we can resolve at all. So this is just to make the point that these mid-lithospheric discontinuities do exist. They are a global phenomenon, but they vary substantially. They're not continuous. They're widespread, but it's not like a continuous layer. And also their amplitude varies a lot. So amongst the hypotheses that have been proposed for them, some people have suggested a decrease in mantle depletion. That doesn't work. The reduction in velocity is not big enough. Other groups have proposed that they could be created by a rotation in azimuthal anisotropy. That can't be ruled out. But for example, when people have tried to see, is there a one-to-one correlation between the isotropic change we're seeing with the scattered body waves and anisotropy effects, there's been some correlation in some areas, but not in others. So it could be an effect, but it's not a complete answer. Shun Corrado and others that work with him have suggested that it's a grain boundary effect due to relaxation of the grain boundaries by anelasticity as the grain boundaries slide. This, has some potential, but the difficulty is it tends to produce a single global boundary that varies relatively little in depth. And this model, in its simple form, has difficulty capturing the complexity we see in the depths and amplitudes of these phases. So another hypothesis is that these are basically layers, the tops of layers of relatively volatile rich minerals, minerals like amphibole and phlogopite, that have been created by metasomatic reactions in the body of the cratonic mantle. A number of groups have explored this option. So for example, on this plot here, here's temperature, here's depth. This line represents the carbonated peridotite solidus. The colored symbols represent pressure and temperature conditions for mantle xenoliths. And so you can imagine from a fairly wide range of cratonic geotherms, you could have low-degree carbon-rich melts that rise through the body of the cratonic mantle. But then when they hit this kink in the solidus, they basically cool and crystallize and can produce these volatile rich phases that could produce the layer whose top we're seeing. So much remains to be learned here, but those are some possibilities. And then this is just illustrating with the profile from RSSD. This is about as big as the velocity drop associated with MLDs ever gets. And one of the nice things about the Bayesian inversion we use to achieve this profile is it gives us pretty clear constraints on the ranges of acceptable velocities. So this is at 90 kilometers. These are the velocities at 115 kilometers. And there really is a pretty well-resolved shift between a low velocity layer and a high velocity layer. So this shear velocity, this absolute shear velocity, is consistent with reasonable compositions for background depleted mantle. And then if you introduce the minerals, amphibole and phlogopite principally, from experiments that show the crystallized products of volatile rich melts, you can, in fact, produce this 6% velocity drop pretty nicely. So this model does seem to work. But as I said, there are multiple explanations that are out there as alternatives. Okay. Now, on to Alaska. Okay, so I wanted to show some new work, partly because it's a cool tectonic story, but also because it illustrates a lithosphere-asthenosphere transition in a very different environment that informs our global understanding of what that boundary looks like. So what I'm showing you here is basically a kinematic model based on GPS data for how the surface of the plate is moving in Alaska and adjacent Canada. And basically what we see is subduction in the south, but then in the north, we have these southward directed surface motions. And so now if you look at this rendered as kinematic strain rate, the blue axes show compression, so you have compression of the upper plate where the plate is subducting. But then in the northern and interior part of Alaska, you have these southward directed velocities, and the origin of these is somewhat enigmatic. So to try to get at this question, Isabella Gama, another wonderful graduate student at Brown, has been doing joint inversions of Rayleigh wave phase velocities and S to P phases at stations in Alaska. And to date, she has results for stations at each of the colored points in this map. So this is just illustrating a station from central Alaska. So here we have a relatively thin 70-kilometer thick lithosphere, and then a well-resolved decrease into an asthenosphere. If you go further north to this station here, the overall thickness of the lithosphere is greater, and the velocity contrast with the asthenosphere is less. So in this map, we're showing the depth of the lithosphere-asthenosphere in transition, which is basically the midpoint between the lithosphere and the minimum velocity in the asthenosphere. And what you see is that here we're getting points that represent the base of the subducting plates, sort of between 80 and 110 kilometers thick, very thin lithosphere in central Alaska, and then much thicker lithosphere in northern Alaska. So this has also been documented by studies that primarily use surface waves to get at lithospheric thickness, but what's new about this study is the converted body waves give us a much tighter constraint on what the gradient between the lithosphere and the asthenosphere looks like. So this is now the same plot of lithospheric thicknesses. This is now looking at the minimum velocity in the asthenosphere, and what you see is where you have the really thin lithosphere above the deeper part of the subducting plate is also where you get the minimum asthenospheric velocities. So now I'm going to show you results on two profiles, profile AA prime and profile BB prime, and these are running over the lithosphere that's subducting in this part of Alaska. So this is now profile AA prime, so this is from the south to the north in this direction. These contours show the slab seismicity that defines the upper subducting plate. And each of these colored points shows the depth of the lithosphere with its associated error bars. And again, here's this band of really thin lithosphere right above the subducting plate. As you move further to the north, the lithosphere gets thicker. This is also the zone where we get the lowest velocity asthenosphere. And we see a similar thing on this other profile. So thinnest lithosphere, lowest velocity asthenosphere, and then much thicker lithosphere in the north. So this actually makes a lot of sense with our understanding of how subduction zones behave. So presumably we have the subducting lithosphere. It's dehydrating and releasing fluids into the asthenosphere and promoting melt. So indeed, we would expect the lithosphere to be thinner here and the asthenosphere to be lower velocity. But what's very nice about this study is we can now actually track the northward extent of that subduction zone modification of the upper plate. So clearly subduction processes are modifying the upper plate heavily in here, much less so further to the north. So that illustrates that this would be the band where we would expect the lithosphere to be thinnest and weakest. And this actually correlates really well with models of surface deformation produced by geodynamic models that combine coupling of the subducting plate to the surrounding mantle that Lucy Flesch and her group have been calculating. And basically, it suggests that this weak lithosphere in here is a zone that's compressible that allows that southward directed surface motion to be particularly pronounced in this part of central Alaska. So one of the things we're going to be working on further in the future is combining our constraints on viscosity from the seismic models and directly incorporating them into her geodynamic models to see if we can bring those GPS data into even better agreement with the geodynamical calculations. Okay, alrighty. So now I'm going to transition to talking about the oceanic lithosphere. And these results are hot off the press in the sense that we really decided what we were seeing like Friday. So I know this is being recorded, which makes me a little bit nervous, but let me just give this to you with a caveat that these are very new results. But I'm pretty excited about them, so I wanted to share them today. But just take them with that caveat. So you can see from these 2 points here that we can actually see the base of the subducting plate, the subducting oceanic lithosphere with S to P phases as well. So these are just 2 stations on land in Alaska, but because of their conversion points, we actually can see the base of the subducting plate as it subducts beneath Alaska. This is just to give you the idea that we do get converted waves, and we can also get reflected waves off the base of the oceanic lithosphere. Okay, so now let's talk about the oceanic lithosphere. So just to get oriented, this plot here shows profiles of absolute velocity for different averages globally of different ages around the Earth. So the blue lines here show the cratons. This yellow line shows the global average of Phanerozoic regions. And this red, actually the sort of red to orange line here, these 1, 2, 3 profiles, these show averages for oceanic lithosphere of 0 to 25 million years, This one is 25 to 100, and this is more than 100 million years. So this is a beautiful model, and it shows what we've known for many decades now, that if you look at surface wave models, indeed you see what seems to be the thickening of the oceanic lithosphere with age as you move from ridges where it's young to the edges of the ocean basins where it's much older. But surprisingly, even though you would think we would understand the oceans because they have a simpler thermal history than the continents, there's actually a fair amount of controversy about the degree to which this cooling is reflected in the oceanic lithosphere and how it's reflected. So to illustrate this point, I want to show this figure from a recent review paper from Kate Reichert. And what I want to illustrate here is the difference between these black lines. So these show the isotherms. So this is age on this axis, and this is depth on this axis. So these are isotherms for a cooling plate model. And then the dashed lines show the isotherms for a half-space cooling model. So in a cooling plate model, you say, OK, there is a thickness, an asymptotic plate thickness, beyond which I am not going to let my plate grow. So you're basically pinning the maximum thickness of the cooling oceanic lithosphere. And in this case, it's about 120 kilometers, versus a half-space cooling model, where basically you just let the oceanic lithosphere thicken with age infinitely. OK? And then also on this plot, all of these points represent different observations where you either have a converted phase, like an S to P phase or a P to S phase, or you have a reflected wave that's bounced off of some kind of contrast in velocity within the oceanic lithosphere. And you see that there's a band of these that's concentrated for the older oceans at a depth range between about 60 and maybe 90 kilometers. And there have been many, many studies over the last decade trying to make sense of these observations with surface waves. So this is a plot from Kate Reichert's paper. So she's taken the French et al. SEMMA model and plotted averages for the Pacific Ocean as a function of age. So here at young ages, very well-developed asthenosphere, very thin plate. And you can see the thickening of the oceanic lithosphere. And if you track the minimum velocity and say that's the asthenosphere, you end up with a relatively thin plate. That definitely looks like a cooling plate model with a thickness of about 70 or 80 kilometers. But this is then a study from Caroline Begain, 2019. This is taking phase and group velocities from the Pacific, and it's fitting it with their best fitting model. And this is actually a half-space cooling model that contains a layer that's chemically depleted due to melting at the ridge. And this is their best fit model. And you can see that the sort of cool lithospheric layer is much thicker. So both of these fit the data, but it's one Earth, so they both can't be right. So what we wanted to do was to try a simple test that would reconcile Rayleigh wave phase velocities to see if we could reconcile them with these observations of scattering and reflections. Basically, are the Rayleigh waves seeing the same structure that the converted and scattered body waves are? So this is a collaboration between Colleen Dalton, Kate Reichert, and myself. So this is work that Colleen did. So these are now phase velocity measurements, these gray dots here, for the entire Pacific Basin. These are different periods. So this is shorter period, 25 seconds, out to longer period, 125 seconds. And rather than inverting these for shear velocity structure, because when you invert for shear velocity structure, because of the very broad sensitivity kernels, particularly at longer periods, the assumptions you make about your starting model, how you damp your model, how you smooth your model, things like that, can actually have a pretty big impact on your result. Colleen decided just to compare phase velocities. So the gray points are the data. They're from Ekstrom's phase velocity database. And then Colleen took plate models, so cooling plate models, for different asymptotic plate thicknesses from 45 to 145 kilometers. They assume a Hertz per guide mantle. She calculated what the shear velocity structure would look like for that geotherm using perplex, and then from those calculated predicted phase velocities. So we're just comparing phase velocities to phase velocities. There's no inversion for shear velocity here. And each of the colored curves represents a different model. And I think you can see that the data themselves, even though there is some scatter, even from this plot, they rule out certain classes of models. But now when you quantify the errors, you get a pretty clear result. So on this plot, the vertical axes are misfit. The horizontal axes are period. And each of these colored lines represents a different asymptotic plate thickness. So basically, if you're further in this direction, that's bad. And so what you see is that, and these are different, slightly different conditions. So these are for different mantle potential temperatures. So for example, this one assumes a mantle potential temperature of 15 degrees C and a 1 millimeter grain size. Basically, if you look over this whole range of models, what you see is that the shorter period data prefer a plate thickness of about 65 to 85 kilometers, and the longer period data don't really care. So when you put all of this together, the 65 to 85 kilometer asymptotic plate thicknesses fit the best. So then a question is, okay, we've got these plate models. Can they actually explain the converted wave observations? So what then I did was just take the velocity models. So the red line here shows the shear velocity model for a 65 kilometer plate and a 50 million year old age, and I just calculated what the receiver function would look like. And this velocity gradient, much to my surprise, I might add, is actually sharp enough to produce a fair amount of converted wave energy. An 85 kilometer plate, you still have significant converted wave energy, but it's much more distributed because the gradient's more gradual. But certainly something like a 65 to a 75 kilometer plate actually can produce the converted wave energy. So what this shows is we don't need actually a multi-layered structure to explain the oceanic lithosphere. So this is now, I'm just going to sum up. So in this model, and I'm a terrible artist, so I apologize for the schematic, but this is meant to represent the crust. This blue line is meant to represent the lithosphere transition. What we see in the Pacific Ocean, at least, is that the Rayleigh wave data and the S to P data are consistent with a really simple single thermal boundary at the base of a plate which has an asymptotic plate thickness of 65 to 85 kilometers. So no need for special internal layers. It's just a simple cooling plate. Okay, so that's that conclusion. Now let's return to what we saw earlier in the talk. In the younger continental regions, for example, the western US and certainly that part of southern Alaska where the lithosphere is very thin, the transition between the lithosphere and asthenosphere is quite sharp. It's about 30, 40 kilometers in terms of its depth extent. And certainly in the western US, that velocity contrast is large enough that we really require the presence of melt pooled below some regions of the western US, although not everywhere. So this is a place where we must have a little bit of assist from melt at the base of the plate to explain the seismic data. When we get into cratons, typically that transition is very gradual, distributed over 60 kilometers. In most places consistent with a purely thermal boundary. Only in a few exceptional cases do we need an assist from something like volatiles or melt at the base of the plate. And then to look at these mid-lithospheric discontinuities, they are there, they are real. They're probably less than a 6% velocity drop. And as I mentioned, there are many hypotheses out there, but certainly one that's plausible is the idea that they're the collected byproducts of metasomatism. So let me stop there. Thank you very much.
Nice talk, Karen. these mid-lithospheric discontinuities have always disturbed me.
I know.
But one of the ways that you can get out this issue of metasomatism in the lithosphere was done a long time ago by Roberta Rudnick. So you do find metasomatized xenoliths, but you don't know whether they represent 0.001% of the lithosphere or 10% of the lithosphere. And she did it by potassium and heat flux. So do you know if there's any correlation between heat flow in the areas where you see these and in the areas where you don't see these?
That's a great question, and it's one we've thought about. And the answer is we don't know if there's a correlation. And the problem with that is that if you look at where actually heat flow measurements exist and where we have well-documented enough examples that we think we're representing sort of an aerial average in a reasonable way, it's ambiguous.
Yeah.
But I think that would be an excellent thing to do in the future. I want to stress that these are intermittent. So it's not like every craton has them ubiquitously. In Hannah's more recent work, they seem to be stronger at the peripheries of cratons where there have been sort of later tectonic events. That's not true everywhere, but that's true in many cases. So in terms of it really being a heat flow problem, I don't know the answer, but it may be that they are discontinuous enough that they're not a big thermal effect.
I guess there's also the issue too of timing, and like in the Western U.S., for example, these could be laramide or 30, 50 million years, something like that, and it may not be enough time to change the heat flow at the surface if you're intruding these at 100 kilometers or something like that.
Yeah, no, that's a great point. So there's one example I know of where people think that they've dated something like one of these. So there's a study, I think it was Hopp et al. 2008, from the edge of the Kalahari Craton, where I think they dated it to mid-Proterozoic, sort of orogenic event at the edge of the Archean Craton. But it would be fantastic if there were more sort of observations of field samples that actually represented these that could in fact be dated so we could put together a thermal history. Because I think there's still, first of all, a lot of uncertainty about whether this is a viable model, and then secondarily, how much of this relates from the formation of the craton and how much of it is due to later metasomatism.
Yeah. Great talk. I was pretty interested in your station called, what was it, the EYMN station. It's almost on top of the mid-continent rift, and Suzanne Vanderlee's data shows a pretty broad effect in, I guess, P-wave velocity tomography in that region. You didn't seem to pick up any of that magmatism or rift fill. And Karin Smith has looked at diamonds from Atawapiskat, way far away from there, and picks up all kinds of overprinting in small xenoliths that she ascribes to the mid-continent rift. Do you know why you didn't pick up any effect of all that basalt there in that region?
Yeah, so in terms of the basalt, that would really affect the crust largely. And to be honest, I haven't looked at our crustal model there to really tell that for sure. I think that station is not right on the rift. I think it's off the rift.
A little bit to the left,
yeah,
or to the northwest.
So I'm not sure. I'm too worried about not seeing sort of the thickening of the underplaning of the basalt in the crust. So I think what might be going on there is that is a station where we see zip mid-lithospheric discontinuity. That is about as high velocity mantle as you can get. And this is like going way out on a limb speculatively. But it is next to a region where there's actually a pretty strong mid-lithospheric discontinuity. And in my wilder moments of imagining, I almost wondered if the heat from the mid-continent rift actually sort of reactivated this possible volatile rich layer, and they've left the system, and that's why we don't see it there. Basically, the rifting event burned out the mid-lithospheric discontinuity. Mm-hmm, mm-hmm, mm-hmm. Excellent.
Great talk. I have a couple of questions. Well, first, a quick one just to follow up on that. How far away are the actual conversion points um, for the station that we were just discussing with the mid-continent rift? And because I forget what the distribution of earthquakes is in that appropriate for that region.
Yeah, so for all of the one-dimensional inversions, we're using narrow back azimuthal bends because we didn't want to do a whole average around the station because we really wanted to get local measurements. So that is, let's see, so that feature is at a depth of like 80 kilometers. So the conversion points are probably 90 kilometers away from the station. Yeah, so they're not, I mean, you have a good point, they're not directly beneath the station. But when I was talking about this business of burning it out, they actually project to a place where they'd be pretty close to the mid-continent rift.
Okay,
Yeah.
cool. So I have two questions. One is related to this in the Western United States, the process that you were talking about, and I'm really interested in this time scale of 200,000 years for the lithosphere to kind of like retrieve its fast VS, if my memory serves me right. How does that work out in terms of like how quickly you would expect melt freezing to occur or something like that?
Yeah, so I think it's fine because, so what we're talking about is the length scale of the magmatic intrusion into the lithosphere. So we're not talking about regrowing a whole new thermal lithosphere because for a 100-kilometer thick lithosphere, or say 70-kilometer thick lithosphere, we'd be talking like 70 million years, and so that's not viable. But basically, the time scale it's going to take to thermally heal the lithosphere from magmatic intrusions depends on how wide those intrusions are and how they're distributed. And that's, quite honestly where the wiggle room is, because if you make them small enough, you can cool them really fast.
Yeah, that sounds like a really interesting modeling problem.
Mm-hmm.
I have the other question. Sorry, guys, to take up all the time. Is for the Pacific Ocean. So the surface waves that I'm just trying to like make sure I understand the argument. For the long periods, I'm really surprised. I may be misunderstood, but I'm surprised that at long periods there is no age trend, essentially, because if you look at a map of 200-second Rayleigh waves, I thought there would be.
So that's a good question. So just to make it sort of clear what's going on, all of these models have an age dependence built into them. So all of these are cooling plate models where you have thin lithosphere, like zero thickness lithosphere at 0 million years, and then they all get thicker with age. The only thing we're changing is how thick they get at infinite age. So what I'm saying is the longer periods don't care whether they get to, well, nobody likes a 45-kilometer thick plate. So like we can rule that one out. But once you get to like 65-kilometer thick plate, if we look at these points in here, so 45 kilometers always has a somewhat higher misfit, but this group in here are all the other models. So the age dependence is built into them. So like that trend in SEMMUM2, or the trend that Don Forsyth documented in his 75 Ph.D. thesis, that's in here. All I'm saying is how thick the plate gets at really old ages. Once you get to 65 kilometers, the long periods don't care.
So below 65 kilometers, in the 65-kilometer thick plate, velocities don't vary with age.
Correct. Yeah.
But above they do, and so they also affect the long period.
Exactly. Exactly.
So I have a question about this too. I really enjoyed the talk, by the way. This is an average for the entire Pacific basin. Do you think that, or do you have an understanding of what the range would be, the full range of the sort of spatial variation in this depth?
It's significant. Let's see. I didn't put that figure in the talk, but I mean, you can kind of see it in the let me see if I can go back, in the phase velocities. So these gray points basically represent phase velocity measurements for different places in the Pacific. So we haven't like binned them as a function of age. So when you look at, say for example, at a period of 72 seconds, and you look at all of the points in the Pacific Ocean that have an age of 50 million years, this gives you like the total range, and it's big. Now, your eye is drawn by the outliers. If you actually sort of look, if we plotted this as a heat map, you'd see that most of the data really are lining up on these curves. But there are definitely significant variations. So what I'm showing you is definitely a very average property. There are big exceptions to that on certain corridors. Also, so people have debated whether at ages of 80 million years and older, strange things start to happen to the Pacific lithosphere because of the interaction with hot spots or small-scale convection. So we actually redid this calculation only fitting the models to ages less than 80 million years, and you basically get exactly the same result. So it's not like this is being thrown off by weird old lithosphere or something like that. But to your original point, which is there significant variation, the answer is yes.
So do you think then to explain some of these, to explain the full variation, you might have to invoke some of these more exotic
Yes.
plate model?
Yes.
Any other questions?
Okay, I'm never invited again. So now, okay, so now that we have this plot, I'm trying to understand the young ages. So why would there be differences in VS for short periods for young ages between the different models? Because they're all cooling the same from the top down, right? So at age 0, that doesn't matter what plate thickness you have. Shouldn't they all have the same velocity?
So what I should say that what we did here is for each model and for the phase velocities, there's a mean value taken out of it. So you're losing the absolute values to some extent. So the spread that you're seeing at 0 age is a byproduct of that. I should have mentioned that, but yeah. So for 0 age, they should all look identical. The asymptotic plate thickness actually affects the isotherms in pretty significant ways, even for the relatively young ages. So it doesn't have to be very old for the models to start to look quite different.
All right. I guess Karin will be here for the rest of the day. I think we're probably taking off around 5 or 5:30 for the airport. If you're not already signed up to meet with her, please come to lunch. We will be there shortly. And let's thank Karin again.
And thank you all for great questions.